Hi, this is Kjetil. Welcome to my lecture on stability enhancement. The lecture is intended to cover some of the material from chapter 10 in the textbook, and I will mostly focus on stability enhancement related to damping. I will do that by first doing an introduction about stability analysis in large multi-machine system and explain why damping is important. Then I will go into power system stabilizers and try to explain what it is, the purpose, how they work, and a little bit on how to tune them. So first, a little presentation about stability analysis in real system and why this is important. The important thing is, as you know, that low frequency power system oscillations are not just a local problem, and they arise as generators or groups of generators oscillate against each other in different areas of the interconnected grid. The state of operation, meaning the distribution of production and load, the load level, and so on, has certainly major impact on the damping in the system, and thus it's of utmost importance to know the limits, of course, when the damping becomes too low. I'd like to add that tools for damping studies, in small signal stability analysis tools that you know from Power Factory, they're quite specialized and not sort of an everyday tool for power system analysis. So it's good to have that in mind. The case study is related to something you heard about before, I guess. I often use the example of the what we call the Hasle corridor, which is the main transmission corridor for power exchange between Norway and Sweden, and it is important for the power market that sufficient capacity is available, right there. Congestions have obviously negative effects on the power market and the formation of prices. When it comes to setting the transfer limit, there are several constraints that has to be taken into account. Thermal capacity limits is obviously one. What in the longer term, how much current you can actually transfer on the lines. The other constraint is more related to stability. Voltage stability is one thing, and angle stability. And when we say angle stability, obviously we mean both transient stability, large disturbances, impact of that, and damping, of course. This is an overview map of the Nordic transmission grid, and I want to focus on the area around southern Norway and Sweden, where you see the two lines crossing the border from Hasle to Borgvik and Halden to Skogsæter outside Gothenburg, which is the Hasle corridor, so to say. The power flow through that corridor is very much depending on the production in western Norway, at the Hallingdal corridor, as we call it, and the Flesaker corridor, and of course the load in the Oslo area. So transmission limit is usually set as a function of these loading criteria here, and as you see, that the thermal limits remain kind of constant, because the thermal limitations are usually mostly dependent on temperature, but the stability limits can depend to stronger or less degree on the loading condition. And of course, the aim, sort of with respect to stability enhancement, is to raise the stability constraint limits towards or beyond the thermal limit then. So a lot of analysis have been done, and this is an example of an analysis where an eigenvalue assessment has been made for the Nordic model, and this focuses on the electromechanical modes only, and we see in the complex plane where a plot of eigenvalues. Very much of these dots represent natural modes of generators, but if we look down on the lower right end of the slide, we see that there are a few very low damp modes in the range of 3 to 6 radians per second, and that corresponds to 0.5 to 1 Hertz. So these are the issue, of course, that we really want to damp to improve the transmission capacity. And these are, as you know, different kinds of modes, and these low frequency modes are usually the inter-area modes. And if we look at more into this analysis, we very often see that we have a mode around 0.3 Hertz and another one around 0.5 Hertz. The mode shape analysis tells you a lot about what kind of mode it is. And you see here for the 0.33 Hertz mode on the mode shapes that it's mostly observable in Finland, and all the Finnish generators oscillate sort of against the rest of the system. But southern Norway as the most pronounced. 0.5 Hertz mode is a little bit more complex, but it's mostly observable, I would say, in southwestern Norway, and it tends to be in opposite phase to south of Sweden and eastern Denmark. And then the question is, how does this impact the transfer limit? The next thing you want to do is to analyze how the damping changes with increasing power flows on the corridors in order to set the limits. What you need to do then is to make a lot of cases with different transfer, and then carry out linear analysis, modal analysis, small signal analysis, what you call it, for the different cases. And this is an example where we have increased the power flow from around 1200 megawatts and upwards, and computed eigenvalues and presenting the most low damped eigenvalues here in this picture. And we see that for low power transfers, the damping is okay. It doesn't change much either. It's around 9% for the critical mode, which also from the analysis we know that this is the 0.5 Hertz mode. But if you go beyond 1800 megawatt, we see that the damping on the critical mode drastically reduces. But this is in fact related to the 0.3 Hertz mode, but that is another story. Anyhow, you see that at around 2200 you are in that critical low damping, and which suggests that the stability limit is in that area. Now, of course, we need to verify this by simulation, dynamic simulation, and then using the nonlinear model. And this shows that with the intact grid there is actually no problem. The damping is good, and the oscillations you see is related to the 0.5 Hertz mode, can be read out from this. However, if you do an assessment where you have a contingency, which of course you need to do, you see other picture that in this case here, when the power transfer is like 200 to 400 megawatt above the base case, which in this case was 1800 megawatt, you see that there is a problem. And certainly at 2200 megawatt you are on the verge of instability. To sum up this part, we see that damping is important for actually fully utilizing the power system and to push the transfer limits. Therefore, we need criteria and guidelines for determination of the stability limits that is used in operation planning, and that concerns damping, transient stability, and voltage stability. Now, of course, stability limits are important, but not the only parameters when the final transfer limit are set, so have that in mind. Now we move over to stability enhancement, and of course there are many ways of enhancing the stability, but the most important here is the use of power system stabilizers, and that's the subject, main subject here. Now, first of all, the acronym PSS is usually acronym for power system stabilizers, but you will also hear about PODs, which is short for power oscillation damper. It's basically the same, but the use is a little bit different. Term PSS is usually used for generators, while PODs are used for damping controls on like FACTS devices and possibly HVDC converters. But the purpose is the same, to enhance the stability. Now, first, what is a PSS? And we will limit the discussion here to power system stabilizers on synchronous generators. Here the PSS is part of the excitation system, so it's an addition to the AVR that modulates the input signal to the AVR, to put it like that. And why do we need a PSS? Of course, the aim is to improve damping. That means hopefully pushing some or one or a few of the eigenvalues towards the left in the complex plane. That is damping in the mathematical sense then. It's not easy directly to explain how the PSS on the generator works. Therefore, I usually use this block diagram, which I don't know if Amin have used that before in the lectures, but it's putting together the control loops or voltage and the turbine governing action in the linear one machine infinite bus model. So the important here is to follow sort of the gray blocks, and you see that the damping is influenced through the generator torque, and if that damping is going to come from the excitation system, it has to come through the internal transient voltage, the delta EQ dash. So in the linearized version, we see that in order to provide damping, the EQ dash, delta EQ dash signal has to be in phase with the speed variation. Then it will act in the same way as the natural damping. So that is the main idea. So the task is then to make a signal into the AVR that at a certain frequency or within a certain frequency range make the internal transient voltage being in phase with speed variations. And if you look at this, the delta EQ dash depends on sort of two variables. One is the voltage angle, which acts through the A parameter or A value in our analysis in chapter 4, and through the open circuit time constant TD0 dash. The other influence is through the field voltage, and the field voltage again is influenced by the AVR and the PSS, so that's why we need, that's what we can manipulate. This is not that easy, so I will try to sort of explain in my words, at least my understanding of the figures that you see in the book related to this, and then we focus on these two components of the delta EQ dash. This is from the textbook, where it would illustrate that a certain sort of oscillatory frequency, let's imagine that's 0.5 Hertz, for example, that the variation in electrical power is in phase with the voltage angle, and those are lagging speed variation by 90 degrees due to the swing equation. And we also know that the inherent part of delta EQ dash that is depending on the voltage angle, that will naturally then actually be in phase with the speed variation, and therefore provide a damping because of the negative signs, right, to the damping torque. But the other part that comes from the AVR is without a PSS probably pointing the other direction, because it will typically lag the field voltage 90 degrees, and if that field voltage is in phase with the voltage for a fast AVR, then this has a negative impact on damping. So the main purpose you might see of a PSS putting in that in this picture is to modulate the field voltage, so at this particular frequency the delta EQ dash points towards the left and not towards the right. Then it will provide damping. So that is an explanation of stability enhancement used in the textbook. You can read more about that. It is another picture showing how trying to illustrate these connections and also why the delta EQ dash typically leads or lags the angle and field voltage variation by 90 degrees. So and these pictures, I mean, the picture on the lower right, which is my block diagram, is sort of trying to illustrate the same as those in the book. So before we go to actually the design and tuning of the PSS, let's have a look at how they are actually built up. And it's a matter of filters mainly. The first two filters, A and B, are first a low pass filter and then a high pass filter to actually make up a band pass filter, so that we are only focusing on a certain frequency range. The high pass filter is usually called a washout filter because it washes out the steady state and low frequency dynamics. But the main, as you understood from the previous slides, the main issue with the power system stabilizer is the phase compensation, and that is illustrated here in block number C. The other is the gain, of course, and the limiters that you need to have. But the difficulties is in tuning the phase compensation. We'll come back to that. Just a picture here to give you an idea how the modern power system stabilizers usually is built up, because speed or frequency is, as you understand, the best signal for enhancing stability. So we like an input signal to the PSS that is represent the speed or grid frequency, but this may not be always easy to achieve. So a good input signal is what is used in very many PSS, real PSS compensators, and that's what is called from IEEE PSS2A, type, where the input signal is what is called integral of accelerating power. And I think I will, it may sound sort of complicated, but I will try to explain why integral of accelerating power is a good input to stabilizers. Okay, so let me try to explain why integral of accelerating power is a good input signal. And then we can start with writing out the expression for it. I mean, if we write it this way, it is first the filter G, which is a low pass filter, times the measured signal, measured speed or frequency, plus and here I will use what I usually do, 2h instead of m, but you see it's an integral, so it's the integral of the electric power variations. And then the second part is minus the unfiltered integral then. So, and do remember when we talk about this, the swing equation, the rate of change of speed is always related to the difference between the change in the mechanical power minus the electrical power, right? So if we now look at start at the low frequency part, let's look at low frequencies. Then, since G is a low pass filter, J omega is more or less equal to 1, and then you see that the power measurement terms, the integral of power, they will cancel each other, and the integral of accelerating power will be more or less equal to the measured speed or frequency. So that's good. And if we look at the high frequencies, since it's a low pass filter, then J omega is approximately 0. So what we end up with then is delta omega equivalent, or the accelerating power, being equal to minus actually the integral of delta p dt. And again, we see that if we assume that the rate of change of mechanical power is almost equal to 0, again it will be that the derivative of the integral power is again more or less equal to the speed or the frequency. So the whole purpose is just that for high frequency, when it's difficult to measure frequency or speed, you can use the power measurement and get somehow the same or a good signal. The integral of power variation is then a good signal for frequency or speed. That's the purpose. So then there's only one thing left, the actual design and tuning of the stabilizers. And this is a difficult topic, so we will only give you an idea on how it is done. I mean, in general, when you are doing this, you would need to do eigenvalue calculation, or you need to at least to identify the critical modes and their frequency. Ideally, you should do mode shape calculation so that you can observe the nature of the modes and where they are most observable, and also controllable, of course, because that will design where you have the most effective locations for installing stabilizers. But when you have found that, and you know which sort of frequency you want to stabilize, it's a matter of tuning the stabilizer part. And again, as we said, that is a matter of doing phase compensation. And I will explain the principle on that without going very much into detail, but to give you an idea what you should remember. The phase compensation is about tuning a filter to obtain the phase compensation that you want. And then let's start with the system. You have a system, and your input to that is your PSS signal, and the output is usually the speed or frequency of the system, because that's what you want to stabilize. Now, in order to design the stabilizer, the phase compensation of the PSS, you can do and measure or compute the open loop transfer function from UPSS to omega. Let's assume that you have that and you're able to plot it in a Nyquist plot. Not familiar if you're all familiar with Nyquist plot, but it's a nice way of plotting a transfer function. Basically, at low frequencies, this relationship between UPSS and speed is more or less zero. And when you increase the frequency, you have a certain response, and it may have end up somewhere. So this is when the frequency increases. So maybe, for example, at this point, you have your frequency of concern. Let's say it's 0.5 Hertz or something. So let's say omega d is 2p 0.5. This is the frequency that at the frequency where you want it to damp. So, and I don't know if that's obvious, but if you think about it, if you're going to damp this with a PSS, you need an open loop transfer function that is basically without phase shift from the input to the output. So the PSS need a phase compensation of that much. And let's say that this is 60 degrees. Then you need to design this compensator to obtain 60 degrees. So how I will write the block number C here then is that I will make it like this: 1 plus T1S divided by 1 plus T2S, and I will square this, because when the phase compensation is more than 45 degrees, I would say it's good to have a second order, because then each block need only a 30 degrees phase shift. So what we need to do is make this transfer function so that it provides, each block provides a 30 degree phase shift. And if you look at that in sort of, now we can go back to the Bode plot. This transfer function would start, the magnitude would start at 1, and then here at 1 over T1 it will rise, and then at 1 over T2 it goes back. And then you should make sure that your omega d is somewhere in between here, because if we look then at the phase, you will have The way I learned to do it is like this, but you may have learned it differently. To the asymptote will then go plus 90 degrees and then back. So the actual phase will go something like this, right? So that what we want to achieve is that the phase lead here is 30 degrees. Not an excellent drawing, but maybe you figure out. So the point is to find the parameters T1 and T2 so that we actually get this 30 degrees phase lead. And then I will just teach you a simple way of doing that. First of all, we want T1 to be larger than T2, and we want to make it simple. We can say that T1 is alpha times T2, and the simple algorithm, but you can verify for yourself if you want, is that this to make T2 equal to 1 over square root of alpha times omega d, which is your frequency that you want to damp. And then you can actually compute alpha from this function, 1 plus sine theta, where theta is, since you have a second order, it's 60 degrees divided by 2, so it's 30 degrees, and 1 minus sine theta. And I made this 60 degrees, of course, because I know that sine of 30 degrees is 0.5, so I know that this is 1.5 divided by 0.5, which is 3. And then we have made the tuning actually, because then we have that T2 is 1 over square root of 3 times omega d, and if we say that that is like here, it is 2.0.5 p, so it's p, and then T1 would be 3 times that, and that is the same as square root of 3 divided by p. So that makes the design of that compensator. And then of course you need to verify if you got this right, and you have to tune the gain, but that is more sort of increasing the gain until you see the effect. So the most important is this, or difficult is this tuning of the phase lead. Right. So time to summarize. What I want you to take out from this, or to remember, is why is damping important? Of course, it needs to be stable, but it also affects the transfer capacity and the utilization of the grid. Then what is a PSS or a POD? It's an additional controller or an auxiliary controller that helps provide additional damping. How does it work? Basically by adding damping torque at certain frequencies, but it's, as we saw, not that easy to explain in detail. What is the general structure of a PSS? You should know, you should remember that there is a number of filters. There is a low pass filter, a high pass filter, and a phase compensation part, and a gain, and some limitations of your control signal. And then I don't say that you have to sort of learn in detail how to design and tune a PSS, but you should know about the main challenges, how you could use linear analysis to identify the modes that you need to damp, and modal analysis to find where it's observable, where it's controllable, and then that the design is a matter of tuning a phase compensator, more or less. That's it. Thank you for now.